4 carbons are from the diene, 2 carbons are from the alkene, and these other things come along for the ride. Whatever else is attached has to come along too. But at all points in time, we're going to be forming 6-membered rings with particular reaction. This is a very, very special type of reaction. All these arrows happen at once, and we're not going to push those arrows on any type of exam. But instead, you might be confronted with this particular reaction and drawing the resulting product from it. We have our diene in an S-cis conformation. It's the reactive one. And we're going to take our alkene molecule and we're going to take a trans alkene. Okay, we're going to take a trans alkene. We're going to take a cis diene. This is our 4-electron partner. This is our 2-electron partner, just in this pi bond. And we're obviously going to make a 6-membered ring out of this. So when we start these, we just draw a 6-membered ring. Right? And we can probably think, where I'm putting these 2 little slashes here, this might be a good reminder for which came from which, right? So we got 4 carbons over here. On the left of the molecule, this came from the diene. And on the right end of the molecule, this one came from the alkene. There's other things that are attached here. And something interesting happens. If we start with a trans alkene, the product will also have that trans relationship programmed into where the groups go on. These 2 groups here are trans to one another, and that stems from the fact that we start with a trans alkene. Mechanism is complicated. Again, I'm going to see how we do on time, but you might not get into an exact full explanation why this happens. But you're going to have to be able to recognize and replicate this type of problem. If we switch it, and we use a same diene, but let's this time take the cis form of this alkene acid. So this is a cis alkene. This same relationship, that this is cis, will be reflected also in the product. Why don't you just simply try to draw what you think the product will look like? Right? Just do your best, draw it out best you can, and then you can compare it to what I come up with. Okay. This is a good chance right now to practice what we're doing in real time. Well, you should come up with the cyclohexene molecule, and your groups, the methyl group and the carboxylic acid, should be cis to one another. It's okay if you drew them with dashes going down. That's absolutely fine. I drew them with wedges going up. Just as important that you have these drawn with cis stereochemistry. Okay? So that's the important point about this. Please, try and take a careful note about this and do your very best to recognize this particular phenomenon. There's another very, very commonly used diene in Diels-Alder reactions. It's called cyclopentadiene. See if you can deconstruct where it comes from, right? It's obviously 5 carbons. It's a ring, cyclopentane, but the function group in it is diene. It's cyclopentadiene. And we're going to look at how this particular compound reacts with an alkene. The alkene in these Diels-Alder reactions almost always have a carbonyl group on them. The reason is this extracts a little bit electron density away. This is electron rich. This alkene becomes electron poor through conjugation into slight delta plus here. Okay? So almost all of these Diels-Alder reactions will have an electron rich diene, no electron withdrawing groups on it, and then an electron poor alkene, where there's something sucking electron energy away from the alkene center. That's just one of the common things and features that happens here. The Diels-Alder reaction makes a 6-membered ring. This diene already has a 5-membered ring in it. the product then is going to have two rings in it. This ring stays, and we're going to make a new six-membered ring. And there's two ways to draw this or think about how this happens. Well, let's just draw what the product of this reaction looks like, and then we'll slowly deconstruct it so that we can understand where everything is. What we're going to do is, just give me a moment. No need to rush right now or panic. In fact, I might panic if my whiteout doesn't work right. So take a moment, and I'll slow down now so you can draw this. Take a moment so that you can draw this particular structure that I've drawn here. It's a little bit more complex. I'll put a little whiteout in the back here to indicate that this bond here is in the front of us. Right? There's a bond back here, a little bit obscured behind. I want you to look for the 5-membered ring we started with. I want you to look for the 6-membered ring we made. I want you to look for the new pi bond we formed. I want you to look for the remnants of where the diene was and where the starting alkene was in this particular structure. So in the structure C, do you see where the 5-membered ring translates? Do you see where the new 6-membered ring is? Do you see where the new pi bond is? Do you see which fragments of this molecule came from our diene? Do you see which fragments of this molecule came from our alkene partner? All those things I want you to look at kind of carefully. The new bonds we formed between diene and alkene are here. If we look at the starting cyclopentadiene molecule, it's very, very similar to butadiene, 1, 2, 3, and 4. And the 1 position attaches ultimately to the alkene. The 4 position ultimately attaches to the alkene. And this one just stays. This little bridge here, or this little loop here, this little thing up here, stays with us throughout the process. So it's a little bit more complex that this has a ring where we start. But this has a ring. We're going to make a 6-membered ring. And maybe it's a little awkward to draw this. As long as you draw it properly, even if it's drawn ugly, it doesn't have to be a work of art. You've seen my handwriting. Mine isn't for sure. Just as long as it has these features in it, it shows that it's a proper Diels-Alder reaction. Let's draw a couple more of reactions like this. Let's actually do the same one. I'll use the same diene. We'll use a different alkene partner. Let's take cyclopentadiene. Okay, and let's react it actually with a triple bond. Let's take these two things together, atom, react it with a triple bond. For the Diels-Alder reaction to work, we need 4 pi electrons and 2 pi electrons or p electrons here. So we know that something different about alkynes happens when you have a triple bond versus a double bond. You only need one of these 2 pi bonds. Leave the other one alone. So do your very best. Try and anticipate or draw what this product would look like based on what's in your notes, just looking before what we had a few minutes just before the last example we did. Just put that right side by side with it. If you can draw what you think the resulting product would be of this reaction, where simply added in an extra pi bond in the alkyne.